going on. Ladies and gentlemen, offering an outstanding digital experience is often more challenging with the need to stand out and to make it highly engaging. CRED has been doing it like no other cost effectively in real time systems, and to know how, I invite Mr. Vikas Sharma, Technology Leader CRED India, and Mr. Nikunj Sharma, Senior Engineer CRED India, to give us the download. Could we please have a round of applause for the two gentlemen?
Hello, am I audible? Yeah. Hey folks, this is Vikas from CRED. With me is Nikunj. Very good sessions before us, mostly covering very high level and great understanding of the platforms, how to build them around real-time applications. We're going to change the gear a bit. This particular session is going to be focused for developers. A bit raw on the slides, but that is how it meant to be understood and to be appreciated. And we'll dissect a couple of our real-time applications and we'll see how we have been able to achieve some cost effectiveness while having the better performance out of the system. So the agenda for today's session would be the real-time platforms / applications. We will just talk about a couple of them. We have central entity attribute store, the stream processing platform. Myntra also talked about this. They have their stream processing state store on Aerospike. They also have a feature store on Aerospike. We are just going to dissect these two particular systems in context of CRED, how we have optimized them and how we are currently using them in production and with the workloads that we have. The rest of the slides would follow the same pattern. We'll talk about central entity attribute store. What is it? What were the limitations? Why Aerospike? More importantly for everyone, like choosing a data store is fine, but how do you migrate? How do you do that in real time and without any degradation and having right checks in place? What are the improvements that we saw? And we'll also talk a bit about our stream processing platform and how we implemented stream joins on top of it. So I'll hand over to Nikunj, who will take up the next section and talk about the central entity attribute store.
Hi, audible, right? Thanks, Vikas, for the introduction. So let's get right into it. First things first, what is a central entity attribute store? It's pretty clear with the name. It's basically a store. It stores certain set of attributes for a certain entities. And these entities can be, they can be users, they can be devices, phone numbers, anything that makes sense for a particular LOB. And the attributes would then be the properties that are relevant for that particular entity, right? So our main motivation to create this sort of a platform was to make this data available for all LOBs, all lines of businesses across our organization, and to make this in real time. So now having just a store is not sufficient in an organization where there are a lot of business units. We wanted to platformize it, and so we laid out certain objectives of what this platform needs to do. The first thing that the platform should be doing is to provide the capability to gather the data from multiple event sources. These could be event streams, these could be data warehouses, these could be other databases, even files, right? And once we are able to collect the data from different data sources, the next step would be to probably perhaps enrich this data that we have collected from these sources, or apply some sort of transformations on this input data, which can be then can be converted into a proper attribute value. And lastly, sharing this to across LOB. So the platform basically applies some certain governance as well, wherein there's only a single owner of the attribute who can write that particular attribute. So that gives us some sort of a standardization on the platform. But it can be shared by multiple LOBs to drive certain use cases on the platform. Sorry. Yeah, so while gathering of the data, applying certain sort of governance, making it extremely fast for the attributes to access all the features that we needed to develop in the platform, there are certain core tenets that we needed to follow. One is the unification of the data. So different LOBs have a wide variety of spread in terms of their tech choices. So the data is spread across all sorts of technologies. So we wanted the ability to create a consistent data store so that the definition of a particular attribute is pretty standardized and well understood across different business units. Then scalability, new lines of businesses are growing month on month and every year in CRED. And we wanted the platform to be scalable enough to accommodate the new lines of businesses, new entities that are going to be created, and new sorts of attributes that are going to drive these use cases. Next, we wanted this attribute access to be extremely fast. Not just the access, but also the write, so that we can actually truly deliver real-time decision-making for our clients, which are basically the different units within CRED. And we wanted to do all of that with minimal operational overload. We wanted to make it self-serve and extremely easy for other engineers and product managers to integrate to the central entity attribute store and drive their use cases. And of course, data security and compliance at the foremost. We have to adhere to the compliance guidelines that have been set for us, and the platform needs to take that as the utmost priority. So some of the use cases that we drive out of this platform, personalized campaigns, feature rollouts. The attributes of a particular entity can be used to segment, let's say, users into multiple cohorts, and that can, and then the product managers can basically roll out the products from one segment to another segment and see how the rollout is happening. User experience optimization, dynamic content, personalized experiences to each individual users based on the attributes that are set for them. And then there are a couple of platforms, in-house platforms that we have, A/B experimentation platform, fraud prevention platform, customer support, that can be driven by this entity attribute store itself. So this is how it looks, essentially. If I zoom into the grayed out area, that is the domain of the entire platform. It contains an entity store, contains the entity store service that manages the writes and reads from the entity store. And there are certain deployers. This is the place where the attribute owners, so to say, or the lines of business owners, can connect their data sources to the platform and apply certain setups or specify certain transformation logics within these, which transforms the input data into the attribute values. Right. So if we zoom out a little bit, the data flow is from left to right here. There are a variety of LOB layers and a lot of microservices that interact with the application, driving the user experiences. They emit a large amount of data, primarily to Kafka, but there's some SQS usage as well. And then there are two paths. There is a batch path and there's a real-time path. So in the real-time path, the deployers directly connect to these event streams, and based on the transformation logic that the LOBs has specified, writes to the entity store. In the batch path, the data first lands into a data lake, and then through a variety of batch pipelines, it streams the data into some Kafka topics, which can then be connected to the deployers and written into the store. There's also an ingestion, CDC ingestion from the entity store back to the data lake, so that can be useful in updating the value of these attributes. So it's not a very old platform, but there's been like a couple of iterations into this platform. And the existing system that we had, the entity store was built on DDB and DAX. Right, and there were certain challenges that we were facing for that, primarily being the scaling ability of the platform. There were a lot of writes that were coming into the platform and was growing month on month. And we found ourselves in a situation where we cannot just horizontally scale out DAX. We had to change the node types. We had to enhance the node types to leverage higher CPU for each of the nodes in the DAX cluster. And that required some downtime. And since DAX is a caching layer, it would take a long time for the cache to be warmed up as well, depending upon the throughput that we are receiving. And that would have led to performance degradation, which was not what we wanted. The latencies also in the existing system were just bordering around the SLA. In fact, the write latencies were pretty high. It was a 15 milliseconds P99, not very ideal for our systems. The read latencies were also bordering around what we wanted to have from the system. And most importantly, the cost. It was an exponential increase in the cost, with the store being the principal component. About 50% of the entire cost was going into maintain and manage the DAX and DDB cluster. So we wanted to seek out for the alternatives. We looked around for did a POC with a few other databases, looked around a little bit, And we found out Aerospike to be quite fitting for our use cases, primarily because it delivers a sub-millisecond latencies on the key value lookups, and that too at a very high speed. Cost efficient, hybrid memory architecture led it to be extremely cost efficient for our use cases. Then the data is being replicated across multiple nodes. There is replication factor that can control that. There's automated failover mechanisms, automated rebalancing that ensure that it is highly available. It was compatible as well. We have a diverse tech stack. Currently, we utilize Golang as the entity store service, but we didn't want to stick to that in future, based on the future requirements. So Aerospike supported a diverse range of libraries, client libraries, that gives certain sort of confidence for this to be future-proof as well. Also, the data model, we do not want it to adhere to a specific data model in future. The data models can vary. The attributes can pretty much be anything, and Aerospike Data Store provided that sort of flexibility to us, which was something which was pretty good to have. So now that we have chosen to go with the Aerospike, now we have two stores. There's a DynamoDB, and we have bootstrapped the Aerospike cluster as well. DynamoDB has all the data, Aerospike has none. So we had to migrate the data. But before we start with the execution of this migration, we laid out certain tenets. No downtime being absolutely non-negotiable here. We wanted to serve accurate data. We wanted to serve it fast and reliably and without any downtime whatsoever. We also wanted to keep both DynamoDB and Aerospike. So during the migration activity, both of these databases were up. The migration was happening in real time. And we wanted an absolute data consistency between the two, so that the service knows where to fetch the data from, right? The data consistency would also allow us to be able to roll back to DynamoDB once we have gone to Aerospike, in case the migration, something goes wrong with the migration. And we also wanted the ability to do a phased rollout to Aerospike for being the primary source of reads, starting out with, let's say, a minimal traffic of 1% to up to 100%. And again, this is the common theme. We wanted all this to get done with a minimal operational overhead as well. So we tweaked our code base a little bit, primarily into the service that deals with talking to the entity stores, the entity store service. And this is a little tweak that we did in the write path of our service. So whenever we received any request to update a particular attribute for an entity, as usual, as was pre-existing as well, we wrote it to DynamoDB. But when writing to the Aerospike, we first checked for the migration status of that particular entity. And if it was not migrated, we would enrich that update request with all the data from DynamoDB and wrote it into the new Aerospike store. And that would complete the migration for one particular entity. So all the migrations were happening in real time. So this was in the right path, but there are certain entities for which the writes don't come very often. So in that case, our migration would have extended for a long time. And therefore, we tweaked our read path as well a little bit. Pretty similar. Whenever we got a request for getting an entity attribute, we would first check if the entity is migrated. If it is not migrated, we would just make a repair call. We would take the data from DynamoDB, and the repair operation would just write it to attribute store that will mark it as migrated. So all this migration was happening real time. There was no need to launch ETL pipelines to migrate. So this was what the timeline looked like. Right from bootstrapping the Aerospike cluster, we enabled dual writes and read repairs for a considerable amount of time. And then we started out with the phased rollout from 1% to 100%. That took some time. We were very careful for that. And once the migration was complete, we then switched the data lake ingestion to the Aerospike CDC, which came out of the box with the Aerospike Enterprise cluster. So that completed the entire migration loop for us. And as a final sanity work, we just switched off the dual writes and read repairs, and Aerospike became the primary data store for the entity store service. So all that work, we saw some significant improvements both in cost and in terms of latencies. Our cost reduction was up to 55%, which was what we anticipated also, because DynamoDB and DAX were the major components of the cost earlier on. But we saw an incredible lift in the latencies as well, 30% lift in the read latency and up to 84% in the write latency. So that made our the ability to make real-time decisions extremely fast. So yeah, that's it. I'll hand over the call to Vikas, who will talk a little bit about the stream processing platform in CRED. Thank you.
Uh, Thanks, Nikunj. Just pressing on this particular platform that Nikunj talked about is a T0 platform for us. Most of our CRED's business flows work on top of it. So the no downtime was paramount, and hence we had to do this very detailed migration plan with the right tenets in place so that we can document each and every step and figure out if something goes wrong, how do we revert back and make sure things are stable and the services that are using this platform are not impacted in terms of their business logic and user experience also. We talked about the attribute store, which you can think that it could be used as a user profile service store. It could be also used as a feature store. Like it can be on different variations. It just works on the same data model. We just optimized it for our use case, and we saw a lot of goodness coming out of the system. The second part to that is the stream processing platform that we have at CRED. In the earlier talks, we also, people have mentioned that they are using Aerospike for the state store. I just want to dissect a bit and figure out, just wanted to share why we opted for using Aerospike, and I will use that, I'll use an example or a use case to drive that entire decision. In a nutshell, the stream processing platform CRED looks like this. It's built of 5 layers. 3 layers, starting from the lowest one, is the execution environment where does the workload run. Right now we are AMR, we plan to shift on EKS, but we have an option to run on database streaming also. There is this core execution module which maintains the deployment of the pipelines, lifecycle management, resource allocations, in case any of the runtimes that are going down, we have fallback runtimes, so the lifecycle management restart the jobs on the new runtimes, making sure there is availability in terms of resource availability, and the pipelines can be managed a little easier. Then on the top is our pipeline module, which has control plane, obviously to govern things, as well as an artifact management. We have built a bit of a DSL on top of it, which sort of abstracts out simpler operations like filtering, transformation, aggregations, and the users of this platform don't have to write Flink, Java code or something. We can do it through our own DSL, unit test it and deploy it. The benefit is that with this platform is that we get add-on services that we have built for all pipelines, for all tenants, metric collection, logs, dashboard, audit service. So this span across all 3 layers. And of course, to work, we have a metadata manager that captures metadata for each pipeline, each execution environment, and each execution runtime that we have in the layers. So this is fairly layered architecture. We can replace any layer with anything else, and we should be able to work. We are primarily on Flink, and I'll take one example, which is the CRED's promotion stack, and where we felt the need to use Aerospike in, just escalate, or basically making our platform a bit more usable and have a stream joins as one of the examples of the operators. So in nutshell, as like any other promotion stack, it works like this. There is, in CRED's context, LOB, when we mean LOB, it's line of business. If you're using CRED, if you're on the rewards page, the rewards in itself is one line of business, which caters to offering vouchers and cashbacks to, if you play games and nothing and whatnot. The store is there, that's another LOB. So we have a number of LOBs. All of them have some space or have capability to personalize the content for the user. And some part of that is revenue catering, where we would like to promote certain content on those pages, and that is powered through the promotion stack. In previous or in existing, let's say in the existing scenario, how the promotion stack would work is we'll fire serving events, we'll have user events coming to our data lake. There would be batch jobs that will process and do reporting, as well as calculate feedback signals. Why feedback signals? Because we need to know how our content is performing. Right? It could be a CTR, it could be your CTR, it could be your revenue or basically any conversion that is happening. Uh, and that basically helps the system to correct itself, generate reports, and a lot of other things. The solutions that, the problem with the current solution at that state was that we were on batch. It took at least an hour to process. With that kind of frequency, you can't do any kind of effective budget cap, frequency cap, any real-time relevance checks, and and it just hampers the way you can actually use the promotion stack to deliver better results for your users as well as to the system. So what we thought was that let's complement our batch jobs with real-time streaming jobs. But that would require basically building a stream operator or a stream join in our platform, so that we can mimic some of those joins that happen in batch in real time on streams. Why we need that? Because we need to figure out what impressions and what clicks and CTR is happening on a particular content that is served. Unfortunately, right, to keep the app resources, keep the app network resources lean, we can't push everything to the app, and not everything could be captured in instrumentation. The instrumentation at max can capture certain identifiers. And when we are doing these operations, we need to enrich these user events with the actual information that was served to the end user, and that best to have it in backend. So we talked about why we need a stream join. We want to complement batch jobs. We want to build a join operator, joining on impression ID in promotions context. Impression, whenever a content is served to the end user, an impression is generated, which is an impression ID, and then we can use that as an identifier to join the stream of events. So this was earlier. We had data lake, batch job for feedback signal. We just introduced stream jobs for feedback signal. And that would also push to Pino for some real-time analytics and directional understanding of how the content is working in terms of CTRs and view-through rates. Possible approaches, Flink provides a very robust state store, RocksDB managed state store. It's off-heap, there is disk spilling, there is fault tolerance, windowed operations are available, but it comes with certain limitations, and especially for our use case, because we are doing stream joins between serving systems and the user analytics, where the user analytics events can be latent, and it can take up to hours to receive, because the app can go in background, the events are not pushed, and there are a lot of other edge cases. So we have a relatively large window. There's a lot of context remote serving events. So, and the other part is that the view rates are 30% only, so 60–70% of the serving events are not joined, which is wasted. And we can't actually, in our context, we can't have a TTL, because there could be repeated events from the app that might come, and we need to keep the stream, the serving events in memory for a longer duration. So just an example, right? So for us, if we would do 12 hours to 7 days of relatively large join window, the state store would reach more than hundreds of GBs and closely to 1 TB, which is not manageable in a normal or native Flink state store. The other approach is that we can use a wide column database that provides upserts. It could be HBase, could be Kudu. Just taking one of the examples, like Kudu, you can do that. You can have individual streams writing to different columns, updating the same primary key, and you will have the state in a single record for each impression that has happened. You can have unbounded join. You can have out of order event streams also coming. That will also work with this approach. But the problem is that you have to then tap on the CDC stream to learn what is getting upserted, and it would add another component to actually process the CDC events. Apache Kudu does not provide it, Azure provides it, TIDB provides it, but they're thick stack to maintain. Then we realized that, do we need upserts? We don't actually need upserts, because in all practical sense, there is a concept of fast stream and a latent stream. Serving events have the nature to be arriving to the system much earlier than the user events will. So we can reliably say that the serving system events that are generated would arrive through the stream platform a bit earlier than the user events. So can we can we rely on this nature of these streams and build something that can work for us for a large window joins? So we thought that let's build lookup joins. What are lookup joins? The lookup joins are based on the same nature, all practical sense. Serving systems, serving events would arrive earlier because they are generated from the system which is in the close proximity of the stream platform. They will arrive faster. The user events will take some time to come. What we can do is that we can index the serving system, serving events that are coming from the serving system into a table, fast table, KV store or something, and then whenever the latent events come from the user, we can hydrate them by doing a lookup on those serving events. This provides us benefits in the way that, let's say we have 5-6 events coming from the user that we want to enrich using the serving context, that can be done independently, and they will not really hamper each other. What do we need to do that? We needed an external store with sub-millisecond latencies, reliable, strong consistency, horizontally scalable, and cost-effective and operationally simple. Candidates, DEX plus DDB. We learned our lesson from the central attribute store that it's going to be quite costly for us. Same with Elasticache. Then we looked at Aerospike. Aerospike worked for us because it has hybrid architecture in terms of just storing the keys in memory and the data resides in the disk. And with that also it provides us some millisecond latencies. So this basically, this is what we built then, where we have two set of jobs, which is one is ingestion, one is lookup. The promotions serving system or any other serving system would push events to our ingestion platform that will push to ingestion job, which will index to Aerospike. The events coming from the applications would come to ingestion platform, push to lookup jobs. They will enrich using Aerospike. Enriched data goes back to our ingestion platform and goes back to promotion serving for real-time feedback. And then it can be, then we are fanning out to Pinot for doing directional reporting on how the CTR is behaving for each of our content. Just taking an example, these are not actual numbers, just to ease out the calculation, I wanted to focus that on how we did data modeling for this particular use case. It would change depending on what type of events you are joining. For us, whenever a page loaded, we were serving 40 content with each page request from our system. That is promotions and personalized both. So 200 on average page request, 40 content served per request, 8,000 content served per second with 3x peak. The impression rates or all the user events generated on those content around 2,000 to 3,000 on an average and 3x peak. So if you think, if we were to index all the serving events that are generated per content card getting served, that meant that we will have around 350 million keys on an average per 12 hours. And it could actually grow to 1 billion on a high scale day. And that would require around 120 GB of RAM with the application. Doable with Aerospike, but bit costly. And for doing this, what we leveraged was Aerospike's map CDT, because the nature of serving event was that one request has 40 impressions. So we changed our primary key to request ID and made hash map or map CDT where the impression ID was actually the impression ID corresponding to the content served in that particular page. This reduced our write fan outs from 40 to just 1. Each request gets written 1. 3 GB of memory requirement, and the lookups were also fast because we were doing lookups on request cross impression ID. Both of these identifiers were flowing into the user events from the app. We also did a bit of payload compression. We realized that the contents that we are serving, they have a lot of data that or the text that is repeating. So before publishing the data to Aerospike, we did a lightweight snappy compression, which also helped us to reduce 50% of our disk usage on Aerospike. We have covered only two particular systems that our team handles, data at CRED. We also we also handle multiple T0 systems, experimentation, communication, segmentation, metric store, AD, and a lot of these platforms also use Aerospike in various ways. The we also actually handle the data warehouse, which is built on Databricks, on Delta Table, and we are a bunch of curious people. The curiosity scales at around 800 TB of scans every day, around 5,000 pipelines running and updating hundreds of dashboards. We participate in almost 50 plus compliances audits, and we're looking for more curious cases to join us. Please reach out to us on these coordinates if you are interested to work on these scale elements. Thank you.
Thank you very much, Mr. Vikas. We request you to remain on stage, and I would also like Mr. Nikunj to please join. And here we have on stage Mr. Kushal Bansali, Country Manager, Aerospike India, handing over a token of appreciation to the two gentlemen. Once again, could we please have a round of applause for Mr. Nikunj and Mr. Vikas Sharma. Thank you for sharing CRED optimized